This video is part 3 of solving trigonometric equations, and before we get into some examples, we need to understand that there are a couple cases where we'll need to check for extraneous solutions. Check for extraneous solutions. Now, the two cases that we might see of that would be this. If we end up multiplying both sides of an equation by a trig expression, and we'll see examples of when this happens, by a trig expression. If we do that in the process of solving, we're going to have to check our solutions. And then secondly, if we end up squaring, or when we square both sides, so we'll try to get in the habit of remembering when we do these two things, either multiply both sides of an equation by some kind of trig expression, or square both sides in the process of solving. In those cases, we'll need to check our solutions, and just plugging them back into the original equation is all that means to check them. Let's take a look at an example where we want to solve for x being somewhere between 0 and 360, and the equation we want to solve this time is 2 cosine squared of x minus 3 equals 3 sine of x. Now, as you just take a look at what this equation has, you'll notice hopefully something that's concerning, which is we have a cosine expression and we have a sine expression in the same equation. Now, if we're going to end up trying to factor this, as it looks like it might be lending itself to, we'd want those to be the same. Otherwise, we have too many different expressions floating around and no really good way to factor them. So, we can make that happen, given everything we know about all the identities of these trig functions by now. There is a way, isn't there, to replace a cosine squared of x with something that has a sine in it, or a sine squared in it. It doesn't really matter whether I go to the sine or to the cosine direction. The point is I need these to be the same trig function. And since sine of x doesn't really have any good identities, I mean, we could, but they're not as good. Cosine squared has 3 different options. If you take a look at your identity list, or have them all memorized, which is even better, you'll notice there is an option for cosine squared that would turn it into a sine squared expression. Namely, if I rewrite this as 2 times, and then instead of cosine squared of x, I write it as 1 minus sine squared of x. That's just using the Pythagorean identity. And then continue on with the minus 3 equals 3 sine of x. Now notice we have only sine functions in our equation. And let's continue to simplify the left side by distributing this 2. This would give us 2 minus 2 sine squared of x minus 3 equals 3 sine of x. Now, I know that I have a sine squared and a sine, which means this is getting close to the quadratic form we're looking at, or used to by now. But I'd like to get it all on one side and simplified. So let's do that in a couple ways. Let's combine these constant terms. This would give me negative 2 sine squared of x minus 1, in summary. And then on the right side, I still have my 3 sine of x. But now, I would like to move everything either to the left or the right side. But the easiest or most convenient way is for the squared term to remain with a positive coefficient. Notice its coefficient is negative 2 on the left side, but that could become positive if I just bring this entire term to the right side of the equation. So if I do that, of course, I'll bring the negative 1 to follow. That would give me, if everything's on the right side, I would have a positive 2 sine squared of x. I already have the plus 3 sine x over there. and then I would bring the 1 over to say a plus 1 also, and that'd all be on one side equal to 0. Now I could just factor this. It's in the quadratic factorable form. If factoring feels a little rusty to you, again, I might recommend writing this out in the simpler algebraic form of, 2t squared plus 3t plus 1 equals 0. That's really the simpler algebraic form we're working with. And if it helps, you can factor that first without the signs there to clutter it up, and that might look better. But what you'll notice is that if you factor this, you'll end up with a 2 sine of x plus 1 times a sine of x plus 1. And that should work to give us the expression we have here currently. Setting those each equal to 0 would yield that sine of x could be negative 1/2, or sine of x could be negative 1. And again, we're looking for degrees here. If we think on the unit circle, where sine would be negative 1/2, that'd be at these two marks closer to the x-axis in quadrants 3 or 4. And the degree marks for those would be, this is 180 plus 30, which of course is 210. And this in quadrant 4 would be 360 minus 30, or in other words, 330. So those two options work for this branch of the possible solutions. And then the other branch, when sine of x equals negative 1, that only occurs at one place. That'd be where x would be 270 degrees at the bottom of the unit circle. So these three solutions will work for our equation. Let's take a look at another example to solve, and this says cosine of x plus cosine of 2x equals 0. Now hopefully right away you're noticing that the cosine of 2x, the second term, should probably be replaced with an identity. This would be a double angle identity. So if those aren't completely memorized yet, keep that sheet close to you which has them on it so that you can get to know them well. But notice that cosine of 2x has some options to it. It has three options. We prefer, looking forward on solving this equation, to keep all the same trig function present. Notice the first term already is a cosine, so I think I'd like to, if I can, keep the second term, which we're going to use as an identity, still in the realm of cosines. There is a way to do that. So if I copy this down as cosine of x, the first term, plus, and then I replace the cosine of 2x with its identity, which is 2 cosine squared of x minus 1. Okay, so all of that is the identity getting replaced for this cosine of 2x. That's all equal to 0, but now notice the three terms on the left side of this equation, those match up in the quadratic form, so we can do some factoring. Meaning if I put them in descending order, I'll have 2 cosine squared of x plus cosine of x minus 1 equals 0. Now we'll do the factoring of this quadratic-like expression, which will give us 2 cosine of x minus 1 times cosine of x plus 1. Again, double check the factoring with simpler algebra if needed. But then if I set each of these factors equal to 0, I'll end up with the cosine of x equal to positive 1/2, or cosine of x equal to negative 1. Let's just bust out a little unit circle here to get this positive 1/2. Cosine of x, these are x values. Positive 1/2 would occur at the tick marks in quadrants 1 and 4, which are closer to the y-axis. So let me draw all three in each case. I want the ones closer to the y-axis for when cosine is 1/2. Of course, the answers to that would be that x would be either 60 degrees, that's quadrant 1, or in quadrant 4, that's 60 degrees away from the x-axis, or in other words, 360 minus 60, or 300 degrees. So we have a couple solutions there from that first branched option. The second option is when cosine is negative 1. Well, that's only one place in the unit circle at the far left side, so that would be when x is 180 degrees. And so really we have three different options for solutions to this equation. Let's take a look at a third example, and this one states that we want to solve the equation of 4 sine squared of x plus 33 sine of x minus 27 equals 0. Well, hopefully by now you're starting to recognize the factoring patterns of this one and can see that this is in the quadratic factoring pattern. So again, if the factoring is an issue, use the simpler form with just a t instead of a sine of x. But let's see if we can jump right to the factored form for this one. We should be able to factor it as 4 sine of x minus 3 times sine of x plus 9. Now we'll take each of those factors. If you set them equal to 0 and solve for the trig function part of them, we'll get here on the left that sine of x could be positive 3/4, and with the right factor we'll get sine of x equal to negative 9. Now right away the negative 9 should throw a flag. That's beyond the range of sine, so we'll say there's not going to be any solution coming from that branch of this. But now, sine of x equals 3/4. This we can do, but notice 3/4 is not a nice unit circle value. So, since we do want to get an answer out of this, we're going to go ahead and take the sine inverse of both sides, which would mean x is equal to the sine inverse of 3/4. And for this, we're going to have to turn to the calculator. So take out your TI-84 Plus calculator and make sure you're in degree mode, and then let's see if we can compute this. So we'll check the mode. Mode is in degree. Now I want to know what the sine inverse of 3/4 is. So I'll hit the second button and then the sine button for sine inverse. Then I want 3 divided by 4 as my input. Close parentheses. Hit enter. And let's take a look at what we have. 48.6. We'll round to the nearest tenth on these. All right, if 48.6 degrees is our solution, remember that's the one the calculator gave us, but as we've already seen in a previous example, the calculator sometimes doesn't tell the whole truth. So let's make sure we're clear on this. If we draw a little unit circle, let's see where our solution of 48.6 would occur. It'd be in quadrant 1. I'm just going to draw an approximation of where it is. Okay. Now, if 48.6 is our solution, and we only want solutions within one wrap of the circle, it's not going to do any good to add the period of sine to this, which it would be 360, because that will take me beyond what I want. I only want an answer between 0 and 360. But what we have to do is use the symmetry of the circle to see yet another hidden solution. Remember, sine values should be the same in quadrants 1 and 2. They're both positive there, and symmetrically there should be some similar values. So if this first solution is 48.6 degrees rotated from the x-axis counterclockwise, then there should be a symmetric solution in quadrant 2 that I could find if I rotate the same number of degrees from the x-axis in the opposite direction. So if I went 48.6 degrees counterclockwise, I'm going to now go 48.6 degrees clockwise, but starting over here at the left side of the circle, which by the way would be 180 degrees. So if I do 180 minus 48.6, that would start me over here, take me back to this point on the circle. Well, the sine value there, which remember is the y value, symmetrically would be the same thing. So that means this would be another solution. So 180 minus 48.6 turns out to be 131.4 degrees. And so that does have to count as one of our solutions. Notice the calculator did not give us that answer. We had to use what we understand about the circle and its symmetry to find it. Let's take a look at a fourth example. This one reads, sine squared of 3x plus 6 sine of 3x plus 5 equals 0. Now, it doesn't take too long to notice something very different about this one, which is the inputs are 3x instead of just x. Otherwise, this is in the nice quadratic form that we've been seeing and can factor by now. But that 3x may pose a problem. So we could either just kind of leave it and ignore it, but there's also another way to handle it, which is to use a substitution. We'll say let's let alpha be equal to 3x. Now really this is just a little bit of smoke and mirrors to hide what we're looking at so that it looks more familiar. Let's go ahead and rewrite the original equation but with an alpha instead of a 3x. That means we have sine squared alpha plus 6 sine of alpha plus 5 equals 0. Okay, but now it's in a much more familiar form where we can just factor this as a quadratic-like equation. This will give us sine alpha plus 5 times sine alpha plus 1. And then, of course, we'll set each of those factors to 0, which will give us the following. Sine alpha could be -5. That's a problem. Remember, -5 is beyond the range of sine, so we'll say there's not going to be a solution coming from that one. Or sine alpha equals -1. Now, -5 is a problem that's beyond the range of sine, so we'll say there's not going to be a solution coming from that side. But sine of alpha being -1 is fine. In fact, if we're using degrees, we'll say that alpha could be 270, so that the sine of alpha is -1. But remember, nobody really knows or cares about alpha, because our original problem did not have an alpha in it, it only had x's. So what we have to do now, in order to make our substitution legal, is put it back. In other words, if alpha is equal to 270, which we found correctly, we know that alpha is really 3x. Okay, so this means that 3x equals 270. Now we'll solve it for x by dividing by 3 on both sides. This will give us x equals 90 degrees. But then here's where there's another snag when your input is not just a simple x, like we had a 3x in this case. So we kind of got by using this substitution, which made things look a little prettier along the way for solving it, at least by factoring. And then we were able to put the alpha back to be 3x here, but it actually changes something. If you remember back to our graphing days, what would this 3 in front of the x change about the sine function? That's right, it would change the period of it. So let's recall, that'd be like the b value of 3. So really the period of sine for this equation is the pure period of 2 pi divided by b, which is 2/3 then, or 2 pi over 3. Now we're working in degrees, so let's kind of stick with that. 2 pi over 3 would be 120 degrees. Okay, so that's the adjusted period for our sine function, given that there was a 3 in front of these x's. The reason that matters is, remember that our solutions are all supposed to be within one wrap of the circle 0 to 360. If I take the solution I already have of 90 and add, let's say, like the pure period of sine, we know that's 360. If I add 360 to 90, I'm already way beyond one wrap of the circle. The problem is 360 is not actually the period of these sine functions because of that extra coefficient of 3. We just found over here the period is actually 120. So if I add 120 to my original solution here of 90, I'll get another solution. So 90 plus 120 would end up being 210. Notice that's still within one wrap of the circle. So actually that's a valid solution. And I would keep doing this and as long as I stay within one wrap of the circle. So I'm going to add 120 to the second solution of 110, which would take us to 330 degrees. And notice then, that's where I'll have to stop. If I add 120 again to it, I'll certainly be beyond 360. So we had to account for the adjusted period of 120 in this case to be able to make sure and get all solutions to this problem within one wrap of the circle. Let's look at a fifth example of an equation to solve. This one reads cotangent squared of x equals cosecant of x minus 1. Now, as you might recall, cotangent and cosecant are both defined by sine or cosine. So let's actually convert them to that form to take a better look at this. Cotangent is really cosine over sine, meaning cotangent squared of x is really cosine squared of x over sine squared of x. And then cosecant is 1 over sine, so we'll write that as 1 over sine of x, and then minus 1. All right, so really this is an equivalent form of the equation we were given originally to solve. And as you might suspect, anytime you have an equation with fractions in it like this, it's a pretty good practice to clear the fractions or get rid of them. And we could do that in this case as long as we multiplied both sides of this equation by the LCD of the denominators. The LCD of the denominators sine squared x and sine x would be sine squared. So if I multiply by a sine squared of x on both sides, that will help clear the fractions. Now, before we do this, remember, when you multiply both sides of an equation by a trig function, we must check our solutions to make sure they actually work. All right, so when we finally get some answers, we'll go back and check them to make sure they work. But this is a case where you have to check for extraneous solutions because we're multiplying both sides by a trig expression. All right, now let's go ahead and do the multiplying of the sine squared on both sides. I would distribute it to both terms on the left side and just multiply on the right side. Notice the sine squareds would actually completely cancel on the left side, leaving us with cosine squared of x. On the right side, if I distribute the sine squared, one of them would cancel with this sign down here, giving us just a single sine of x minus, and then if I distribute it into the second term, I'll have minus sine squared of x. Now notice we're working with two different trig functions, which is dangerous. We know we have to get it all to one of them. All right, so we have a cosine on the left side, cosine squared, then we have a sine minus a sine squared on the right side. We'd like to work all with one particular kind of trig function, either all sines or all cosines. Now you might find a couple different ways to make this happen. For instance, you might think of converting this cosine squared on the left side to being maybe 1 minus sine squared. That'd be using the Pythagorean identity. And then you'd have all sine squareds and you could combine like terms. That'd all work fine. But I'm going to take maybe even a slight shortcut from that. What would happen if I add sine squared of x to both sides? Okay, so these would cancel on the right side, but on the left side, I'd be left with cosine squared of x, that was already there, plus sine squared of x, and that would all be equal to just sine of x. But wait a minute, what is cosine squared of x plus sine squared of x? That's our Pythagorean identity, which means that whole thing just turns into 1. So 1 equals sine of x. Well, this gives us a pretty clear idea of where to go, right? We want to solve this for x between 0 and 360 within one wrap. Well, sine of x is only equal to 1 at one place. It'd be where x is 90 degrees. And the period of this one is just the regular sine period, which is 360. So adding 360 to 90 would already take us beyond the 0 to 360 range we're looking for our answers. So 90 is our answer. Now we should check, as we mentioned earlier, to make sure that this actually works. So let's go ahead and check our solution by plugging in 90 degrees to our original problem. I'm going to use the second form of the original equation we wrote out, which is cosine squared of 90 over sine squared of 90. I'm plugging 90 into this original equation right here, but the second form of it, just because it's easier to look at these simpler functions than it is with the cotangent and cosecant. So I'm plugging 90 into the left side of the equation, and then on the right side of the equation I'll have 1 over the sine of 90 minus 1. Now, I really don't know if this is true yet. This is what we're investigating. It should be if this is our solution. Otherwise, if it doesn't work, we might have an extraneous solution here. Let's go ahead and evaluate this. Cosine of 90 would be 0, so if you square it, you get 0 over cosine of 90 is 1, but 0 over 1 is 0. So we have 0 on the left side. On the right side, we have 1 over the sine of 90. Sine of 90 is 1, so 1 over 1 is 1, minus 1 is 0. So it works fine. All that means is that 90 degrees is our solution. Let's take a look at a sixth example here, and we want to solve the equation sine of t equals cosine of t plus 1. Alright, so notice we have two different trig functions. We have a sine and a cosine. And we've worked with that. We can, try to turn them both into the same function, either both sines or both cosines. But all the identities we have to do that work best when we have sine or cosine squareds. And in this case, they're both single. But one way to get a squared in the picture would be to square both sides of this original equation. So if I do that, I'll end up with sine squared of t equals cosine t plus 1 squared, which, by the way, we'll have to expand that using our FOIL process. But now, notice I just squared both sides of the equation to try to get these identities working, which means that's one of the cases where we have to check our solution. So when we get to the end, we'll have to plug our answer, if we get one, back into this original equation to see if it actually works. Alright, let's do some of the algebra involved in expanding all this. So we'd have sine squared of t equals, if I expand this right side, remember this is like cosine t plus 1 times cosine t plus 1. That'll be a FOIL process, which could give us cosine squared t plus 2 cosine t plus 1. Now I still want all of the same trig function, but now that I have the cosine or sine squared, it's easier to do that. It seems like the cosines are kind of dominant in what I have, so I'd like to convert this sine squared term into a cosine so I can play with all these other terms on the right side. Sine squared is really 1 minus cosine squared of t according to the Pythagorean identity. So if that equals the right side, which is cosine squared t plus 2 cosine t plus 1, I can now combine all terms to the right side, and if I did, I'd have 0 on the left equals 2 cosine squared t, by adding the cosine squared to both sides, plus 2 cosine t that's already there. And then if I subtract 1 from both sides, those ones actually would totally drop out. So all I have left is 0 equals 2 cosine squared t plus 2 cosine t. Now, as you might recall from some of the algebra we've been seeing, the way we can handle this is by factoring out the common factor of cosine. So I'll say 0 equals, actually a 2 could also be factored out. So if I take out a 2 cosine of t from both terms, I'll be left with cosine of t plus 1. We'll set each of those factors to 0, which means 2 cosine of t could be 0, which would mean cosine of t is 0, or this other factor would tell us that the cosine of t would be negative 1. We can handle both of these. Cosine of t is 0 at a couple places. X could be 90 degrees or 270 degrees to get a cosine value of 0. And then for cosine to be negative 1, that occurs, of course, when x is 180 degrees. So those are the three solutions we have within one wrap of the circle that give us solutions to our equations. But as we mentioned earlier, we have to go back and check them. So let's check them one at a time. First, I'll just go in order here. So 90 degrees being checked is plugging it back in. So is the sine of 90 equal to the cosine of 90 plus 1? Let's see, the sine of 90 is 1, cosine of 90 is 0 plus 1, 1 equals 1, yeah, that works fine. Okay, let's check our next solution, which was 180 degrees, just going in order here. Is the sine of 180 equal to the cosine of 180 plus 1? Well, the sine of 180 would be 0, so is that equal to, the cosine of 180 would be negative 1 plus 1. Yep, that works also. All right, let's check our third solution of 270 degrees by plugging it in. Is the sine of 270 equal to the cosine of 270 plus 1. Well, let's evaluate these. The sine of 270 is negative 1. The cosine of 270 is 0. But, oh, we have a problem. Negative 1 does not equal 1. So that means we have an extraneous solution here, which means we would not count 270 as our answer. So we're going to use 90 degrees and we're going to use 180, but not 270.